Welcome back. In the previous chapter, we discussed about Java platform and the Java platform technologies, the components of Java platform. In this chapter, we will explore the architecture of Java virtual machine. We'll see how JVM is platform agnostic, and thereby we say it's platform independent. So how Java is platform independent, you will understand in this particular chapter. We'll also explore the memory management aspects and look at how JVM manages security, performance, elements, etc. in this particular chapter. All right, so let's explore the architecture of Java virtual machine. So what is there inside JVM, inside Java virtual machine? So if you look at it, so we see that Java source code or the Java program which is basically created will be compiled by a Java compiler. So Java compiler is part of Java development kit. So you get the compiler and it gets converted into Java bytecode, and within the Java virtual machine we do have an interpreter and as well as a just-in-time compiler called as JIT. It will basically compile and immediately start running and creating the bytecode into the machine instructions. So this is what is being done by the JVM. Internally, the native code requires memory, and this is also supplied by the heap memory, which is part of the Java virtual machine, which essentially is nothing but the RAM or memory which is present in the operating system. In order to access this, there are OS specific libraries which are basically being used by the JVM environment. Finally, whenever you need a graphical interface or console, IO, file systems, etc., all these things are controlled by the operating systems, and the JVM internally interact with the OS level libraries and get the relevant data to the program. So this is how a JVM primarily functions. And the features of JVM is it is platform agnostic. So when we are talking about Java, we were talking about the platform agnostic, and we said it's platform independent in the previous chapter. How is it platform independent? So Java source code which is getting converted into bytecode is basically platform neutral. And the JVM, what we discussed in the previous section here in the architecture is available for a particular operating system. So we have JVM for Mac, we have JVM for Linux, we have JVM for Windows. So thereby these JVMs will abstract the respective operating system specific libraries and functionalities, and it will basically create a simple layer for the bytecode to be executed independent of the operating systems. So that is one of the key way in which Java brings platform neutral environment and brings or promotes portability of Java code. And thereby I can use a Windows programming environment or a Windows platform, compile the code and get the bytecode and execute it in Linux environments. It's very much possible. So what is there inside a bytecode? So bytecode is nothing but compiled Java code, as simple as that. And it is an architecture neutral file format, so which is internal to Java environment and can be executed on multiple processors, and it provides a very highly optimized set of instructions. So it is standardized where it basically gets converted into machine independent low level language, the binary language we could say, and solves the portability aspects of Java. And any other security problems that are there is also taken care. So the bytecode is a very important element of Java programming environment and Java applications. So with this, I don't need any additional systems as such for me to execute Java bytecode. All I need is a Java runtime environment. So to execute Java code, I don't need a compiler. So a compiler which is part of Java development kit is required only for the initial compilation of the code, and once it is compiled, all I need is a Java runtime environment for executing this particular code, and the bytecode converts the translated code on the fly. So this is the basic behavior we see and how platform independent solutions can be developed in Java. Next is about memory management. So Java Virtual Machine is also responsible for memory allocation. So memory is basically supplied by the operating system, and we can configure how much memory is supposed to be allocated for this particular Java Virtual Machine instance. And then essentially JVM is nothing but a process which runs in the operating system and manages even garbage collection and prevents memory leaks. So there are various elements when it comes to memory management, which we will explore further in our later chapters. But very important feature of Java, which is a boon for developers, is that they don't need to really worry about memory management. So as a developer, I can focus on writing my logic. I don't have to worry about releasing the memory, etc., which was one of the pain areas in a pointer-based system that we basically had in C++. And this is something where Java becomes more easier for a developer. In addition to memory management, JVM is responsible for loading the classes. So it can dynamically load the classes as well. So we have dynamic class loaders. And by loading the classes dynamically, it will reduce the footprint or memory footprint, which is very important elements, especially in like devices, right? In environments where you are running with very constrained memory, right? On a server side, yes, you may be having a lot of memory, but on devices like a smartwatch where Java is running, you may have very limited memory. So in that case, it is more important that we efficiently utilize the memory. So for these kind of places, dynamic class loading becomes helpful, and JVM is responsible for dynamic loading, which enables extensible and flexible applications as well, which is another important feature of Java application programming. In addition to this, we do have another very important role, which is security. So when you're talking about bytecode, which is platform independent and which requires to be executed in an operating system, JVM is responsible for verifying the bytecode. So it is possible that the bytecode could be having undergone some kind of an instrumentation, or some corruption libraries could be there. If you execute that, there is a possibility of a virus or malware getting into the system. And JVM takes care of that with a concept called as bytecode verifier, and it will validate all the bytecode and ensure that it is valid. So thereby we can basically be assured that JVM is capable of handling this efficiently, and if required, we can also insist signing the code with a proper authority. This is also very much possible. And then it also supports sandbox execution, which means reading and writing local files which are not enabled by default, so that any unauthorized operations can be automatically controlled by the Java virtual machine. So it is not that just you are running a Java program, you can access all the file systems. Not really. So it is also very much important from a security point of view. And then it has class loader, which is responsible for loading only trusted classes. So you can basically specify, that's where the concept of signing comes into picture as well. So you, as a developer, you can say, hey, this is my trusted code. So we see that, like for example, when you install an application in Windows, for instance, you would see, is it trusted? Have you downloaded this executable from a trusted source? Why? It is very important, because it should not happen that you download from some untrusted source and some virus gets into your system or some malware gets into your system. This is something which has to be taken care, and class loader enables a virus-free system in the Java environment. In addition to security, we do have another important responsibility for JVM, which is of course performance. So it has JIT compilation, or just-in-time compilation, where there are a lot of optimization routines and heuristics which are basically implemented to ensure that bytecode is compiled into machine code as quickly as possible and helps in delivering best performance. In addition to this, the hotspot. So the JT compiler brought in two variations of compilation. One is for client specific environment or client applications, which is client compiler, and there are certain optimizations which are there for server side compilation as well. For example, if you are deploying a web application in Java environment, yes, we have an option to use server side compiler where it internally optimizes for compiling the code which runs on a server side operating system, a server side environment. So these are some of the important features that we basically explored in this particular chapter. So we discussed about architecture of JVM and the core features of Java Virtual Machine. In the next chapter, stay tuned to explore Java Development Kit, the core elements of Java Development Kit, and look at how we can use those specific libraries.